Okay, let's settle down. Welcome to lecture 2 for 16A. So today I'm going to, thank you. Today I just want to start with a couple of minor administrative things, and then we're going to get right into our material. First of all, I want to apologize. I heard that there were some students that could not find the right room for my office hours last time, and so office hours will not necessarily be in my office simply because my office isn't large enough to accommodate everyone in the class. And so the room for office hours will always be posted on the website. Please check the website for the office hours. Today we'll be in 212 Corey. We'll try to be in the same room, but because of logistics of room reservations, we might not be able to be in that exact same room. So if you're planning on coming to office hours, please check the website or just walk with me right after class, because if you walk with me, you're guaranteed to go to the right room. That's the first thing. Second thing, we had an overwhelming response to the people who signed up for attending the roundtables, far more than we had anticipated. So we're working on figuring out logistics so that we can accommodate every single person who wanted to attend, but bear with us for a little bit while we try to figure out rooms and logistics to accommodate the larger number of people who signed up. But you should be hearing back about that hopefully by early next week. Last thing, we posted a little tutorial on how to install and run Jupyter notebooks. This will be helpful for you for homework 1. This will also be covered in the first lab section. So for those of you who will be going to lab today and for the rest of the week, you'll get to see this. Some of you didn't have lab on Monday because of Labor Day. So it might be worth it to just quickly look through that tutorial or go to office hours, go to homework party, so that you can make sure that you can do the first homework. The first homework is very light. It only has 2 problems on it. Hopefully it shouldn't take much time, but it has, basically we're buffering time for you to be able to install all of the necessary software on your computers and get stuff up and running, because Jupyter Notebooks will be a big part of the homework going forward. Just to make it also clear, our homework policy is one that really encourages you to try and use the homework as a learning tool. Our homework is not intended to test you, and we really think that doing the homework well is the best way for you to prepare for your midterms and for your exams. And we understand that, sometimes things are stressful, sometimes there's a problem that's particularly tricky. So for the purposes of homework credit, if you do 80% of your homework, this will be treated as full credit, and everything will be scaled accordingly, right? On top of this, you will be getting 1 homework drop because, sometimes you might have to travel, you might fall sick, things like that. So I really encourage each one of you to focus on trying to maximize your learning from the homework. Use office hours, use your discussion TAs to really, see how you can make sure that you understand what the homework is trying to tell you. And if you have questions about this, please ask in discussion, ask on Piazza, and otherwise. Finally, discussion sections will start tomorrow. Please attend a discussion section of your choice. As I mentioned, we have many different types of discussion sections, and we ask that you find one that you think works for you. So we have discussion sections that are targeted towards freshmen, discussion sections that are targeted towards junior transfers. There's a section that is targeted towards students who have had some linear algebra experience. We don't expect you to have linear algebra experience. I want to emphasize that. You don't have to have any linear algebra to be taking this class. In fact, we recommend that you don't. But in the event that you do, you can attend one of these sections. This time, we also have 2 other sections that are different from what we've had in the past. The first one is we're offering 1 discussion section that is 2 hours long. This discussion section will cover exactly the same material as the 1-hour sections, but it will just go more slowly, and it'll give you more time to work out problems yourselves. So if you think you would benefit from a more slow presentation of the material, please try this section out. Finally, we recognize that this is a very, very diverse group of people, and there are people and students and groups within the population of students in EE and CS that are underrepresented. And if you feel that you would benefit from being in a cohort of people, then there's a section that is being run, it's also on the website, that you can choose to attend. It's, I think, here. So the, I think, red, okay, I forget what the legend is, but go, I forget the color labeling. Please go look on the website. It'll tell you which section is which one. Please try and find the section that you think is best for you. I really encourage you in the first week or two to shop around, attend different sections, feel out the style of the TAs. They're all different. They're all amazing. Find someone that clicks with you. Okay, so those were just some little administrative details. Hopefully this is all clear. If not, please ask questions on Piazza or come to me in office hours right after. Okay, so I want to get into what we're going to be talking about today. Today I want to introduce the first module and talk about the imaging lab. And after that, I'm going to talk a little bit about superposition and how you can recover signals from superposition. And I really want to, by the end of the lecture, get to addressing the question that people brought up at the end of last lecture, which is, when you're given a system of linear equations, how do you figure out if you have no solutions, or a unique solution, or an infinite number of solutions? How can we do this systematically, and how can we teach a computer to do this? So we talked last time about the tomography example, right? Where we can use measurements from different pixels in this image, or in this case, in our parts of our body, to be able to, and combine them to be able to recover the underlying image, or underlying, for example, part of your body that you're trying to actually image. And we talked about basically simplifying this to this very simple 2x2 grid, right, where we had 4 pixels. And we talked about taking measurements. And first we took 2 horizontal measurements and 2 vertical measurements, and realized that, oh, actually, you try solving things out, and somehow you can't get everything in terms of the constants. You end up with some variables in your equations. You can't actually solve all of your equations. And so we decided that we needed to take another measurement, right? And then we took a diagonal measurement. And the question was, well, how did we know to take a diagonal measurement? How do we know when you're designing your MRI machine or your CT scan that the measurements that the machine is going to take are actually going to work? You want to know this before designing your machine and selling 1,000 versions of it, rather than after you've sold it and you find out, oh, actually the measurements that this is taking are actually wrong. So how do you design to have the correct kind of measurements? And that's exactly what we're going to be talking about today. And this is actually leading in to the entire first module in the imaging lab. So tomography is one example of imaging, but what is imaging in general? You have some subject that you're trying to image, and you have an energy source. And this energy source is, let's say, illuminating the object, and there's a detector, like a camera, that is then detecting that energy that is being reflected, let's say, from your subject. And this is the general structure of an imaging system. In the lab, in 16A, you're going to be building what we call a single pixel camera. The cameras on your phones have multiple pixels. What we're going to be doing is building a simpler version of this that just has 1 pixel. And what you're going to do is you're going to have patterned illumination that allows you to actually recover the image from just a single pixel. So if there's many, many pixels in the image, and you only have a single pixel, how can you possibly recover, basically multiple unknowns? If you have many pixels in your image, that means you have many unknowns. How can you recover them from just 1 measurement? Right? That's kind of a little bit of a tricky question. What are we supposed to do to be able to do this? And the trick here that you're going to be using in lab is going to be patterned illumination. So, what could you possibly try and do in this case? Let's say you can only measure 1 pixel at a time, and you think of these pixels as basically numbers in a grid, like the way we set it up last time. But you can only get 1 measurement at a time. What would you want to try and do? Yeah? The suggestion was to illuminate different parts of the image, right? So if you illuminated everything at once, you're going to get a bunch of stuff reflected back, and you're not going to be able to understand. But instead, what you could do is you could say, well, I can only measure 1 pixel. I'll only project energy on 1 pixel. That way, I'll only be able to get the reflectance from 1 back. Everything else will be black. Everything else will be dark. I won't see it at all. And that's actually exactly one of the things that you're going to do in lab. But that doesn't seem very satisfying. And actually, it turns out that this can be quite error-prone. It's error-prone because, first of all, it's hard to shine light on just 1 pixel. And secondly, what you get back when you're just shining 1 little bit of light is you get a very weak signal back. There's not a lot of light being reflected back. When you're taking a picture, if everything's kind of dark, there's not a lot of light, the images turn out blurry, right? You can't see them clearly. So to get around this, what you're going to want to do is you're going to actually want to illuminate multiple pixels at once. But when you illuminate multiple pixels at once, what happens? You suddenly have mixing of the signals. You're not getting 1 pixel at a time. And now the question is, what can you do? Can you recover the frog? How many measurements are you going to need? And how should you choose which pixels to illuminate over others? Are there better ways to illuminate pixels? Can you design your experiments as an engineer to be better so that you can recover the image better? That's the question that you're really going to be thinking about. And that's what the entire Module 1 is going to be talking about. So when you're thinking about some kind of linear algebra that we're learning in class, try always to map it back to, for example, the imaging lab. It'll help you, place yourself and might help you ask questions, might help you understand why we're trying to talk about a certain concept. And if imaging isn't your favorite application, there's going to be a lot of other applications in the homework. So pick your favorite application and run with it. So just to give you here, this is a setup for what you're going to be seeing in lab. This will start next week, week 0, or the first week you'll be basically having a Jupyter Notebook bootcamp. You'll hear a lot more about exactly how this is going to work in lab, but I just wanted to introduce this to you and have you keep this in the back of your mind as we start thinking about systems of linear equations and why we want to actually solve them. So with that, I guess this is kind of the big motivation, or tomography I think of as the big motivation for understanding systems of linear equations. It's quite powerful in that, this is potentially life-saving technology. And that's a pretty strong motivator for wanting to solve systems of linear equations. But for those of you who might have started on homework 1, or even as we're going to talk about now, there are sometimes just some fun things that you can do with systems of linear equations that are not necessarily things that are going to be particularly useful, but they might be entertaining. So I know a lot of people in the room are freshmen or incoming transfers, so you might be taking 16A and 61A at the same time. And when we were trying to make the websites for these classes over the summer, we kept running into this issue where this image kept popping up, and it would show up on the 61A website, and then it would show up on the 16A website. And there was all this confusion about, wait, who's the instructor? Who is that exactly? And we knew it was supposed to be Professor De Niro and Professor Boser, but these weird images kept popping up. And we couldn't recover the original instructors, right? We had a measurement on our website, which kept being generated. What do you want to do when you have measurements, but you want to recover something? You want to try and basically figure out what the original thing is. If you have some measurements, and they're not enough in terms of being able to figure it out, all I have is this image, what would you want to do to try and, let's say, figure out what the original instructors actually were? This did not work. If you could do anything you wanted. Okay, yeah, got it back. Well, one idea might be to say, here is basically one mix of the instructors that is being shown. What if I gave you another mix of the instructors? What can you do now with potentially two mixes of instructors? I'm not really asking you to think about reading this code, though I can walk you through it. Basically, what we're doing here is there's an original image, there's two original images, there's two factors, and we're basically taking factor 1 times instructor 1, factor 2 times instructor 2, and we have two linear combinations of these images that are being rendered. Maybe we could have different linear combinations. We can have something like that. What would happen here? You might have different versions if we tried to make this 16. You might have different versions that, depending on the different weights, right? These are different weights that are being provided to these two different images. So when you think about wanting to recover these two images, how many unknowns are there? These are 512 by 512 images. So that's about, I think, 200,000 variables that basically every single pixel is an unknown, right? You want to recover every single one of these. We could do it by hand, but I trust none of you want that as your homework exercise. And so what we want to try and do is figure out basically systematically how can we disentangle these two images. And the way that Jupyter notebooks, or basically IPython, will do this is, let's say we can print out each of these images. And what you see here are all of these pixel values. And I can print out, and I can see the shape of it, which I can see it's 512 pixels by 512 pixels. I can print out the other mixture. And I can print out its shape as well. And now, what I have here is a little bit of just organizational. Just a little bit of organizational code. And what I want to call really here is this function np.linalg.solve. And then I'm going to do that. I have that. I have this. And let's see. I get two answers. Let's see what the answers I get. Oh, I get one nice image. And I get a second clean image. And what did I do here? I basically told this function np.linalgebra.solve that I have basically some measurements, which are in this B vector, and I know that these images are combined by these ratios. Please solve this to give me the original images back. And what we are going to talk about today is what is in the guts of this function, linalg.solve. Because we really don't want to be solving this out exactly by hand. So with that, I want to try and shift to the document camera. Can everyone see this at the back? Yeah, great, thank you. Okay, so you have this image, mix 1, which is some factor alpha 1 times image 1, plus some factor alpha 2 times image 2. And you have mix 2, which is beta 1 times image 1 plus beta 2 times image 2, right? And these M1, M2, these are your measurements or your data. These are the two superposed images that you saw. And what are these guys? Alpha 1, alpha 2, beta 1, beta 2. These are those coefficients, right, that were used to generate the combination. And these are also known, right? So the measurements and data are known. And we want to figure out what were the underlying images. So these guys, image 1, image 2, these are what are unknown. It's important to keep track, especially when you're doing a lot of symbolic math. You might have symbols that are representing variables and other symbols that are representing constants. Constants are known, variables are unknown. It's important to, figure out a way in your head to keep track of these different things. And the way that we solved this, what I did, the little piece of code that we had, what it actually did was it took this image, which is this basically square that is 512 by 512, and it said, oh, look, there's so many little pixels here. All of these is a little pixel, but this is a bit hard to manipulate, and so it transformed these into what we're going to call a vector. And a vector is just an ordered, O-R-D-E-R-E-D, ordered list of elements. And usually we'll write this in a long column. So I'm going to write this as, let's say, a vector x, which is equal to x1, x2, all the way up to xn, where here n is equal to 512 times 512. Okay? And so basically this pixel goes here, this second pixel goes here, this third pixel goes here, so on and so forth, until I put all of these pixels into this really, really, really long vector. You're going to be doing something very, very similar in lab, and so you'll get to understand a little bit more about this. How do you go from things that are organized as a grid into things that are organized in a vector, in a straight line? You'll get to see more about this in lab. But what we want to figure out is now, how do we solve this, right? How do we solve? And what did that function, the solve function, actually do? And I don't really want to sit here and do out a full example with these many variables. It's too much algebra, and we'll never get anywhere. I'll spend the entire time writing out the problem. So we're going to do basically something that we're going to keep doing over and over and over in this class. And if there's one thing that I want you to take away with you when you leave this class, it is, when you're faced with a complicated, large problem, simplify. Make a simple example and understand that. So we're going to do our usual 16A strategy, which is simplify. When in doubt, simplify. It's probably one of the most important things you can take away from this class. Okay. So let me see if I can zoom out a little bit. If I zoom out to this level, can the people at the back still read? No? Okay. Okay, I will zoom in again. Okay. And the simple example I want to think about is the following. 2x plus 3y equal to 8. Let us call this equation 1. and 3x minus y equal to 1. Let us call this equation 2. So we have two variables. We have two equations. Why don't you just take a minute to work this out, solve it, talk to your neighbor, take a stretch break, whatever you want. But ideally, in a minute, try to solve this problem. Feel free to talk. Get to know your neighbors. How many people think they have a solution for this system? Show of hands? Okay. How many people solved this system exactly the same way as the person sitting next to them? How many people solved it in a different way from the person sitting next to them? Right? How many people think that there are probably several different ways that all of you collectively solved this problem? Probably some of you chose to solve for x first, others chose to solve for y first, some of you substituted equation 1 into equation 2, some of you did the other way around. There's clearly many, many different ways to do this, right? But if we wanted to now write a piece of software that would solve systems of equations for us, do we want that software to have different behavior every single time, right? We want it to be reliable, predictable, and we want it to be systematic. So what we're going to talk about is how do we develop a systematic way for solving these systems of linear equations. And for that, let's start doing it together. So first thing that I'm going to try and do is I'm going to try and be a little bit lazy. So I have 2x plus 3y equal to 8 and 3x minus y equal to 1. But there's like some repetition here, right? X shows up twice, y shows up twice. So I'm going to write these numbers in a box. I'm going to put a 2 here, and a 3 here, and an 8 here. And I'm going to put a 3 here, and a minus 1 here, and a 1 here. And I'm going to draw this line. And this is what I call the augmented matrix form for this system of linear equations. It's just a rewriting of the equation where we're ignoring the variables. And we'll see why this is useful, and you'll start to use this more and more as we go along, but we don't even have to think about it so much. But how would we now solve this systematically? What I want to do is I want to say, first, set the coefficient for x to be 1, basically normalize equation 1. So what I'm going to do is I'm going to say I'm going to take E1, and I'm going to divide it by 2, which is going to give me x plus 3 over 2y is equal to 4. I'm going to call this E1 star. Does everyone see how I got E1 star from E1? We're good? Yes? Okay, great. Now, our second step in doing things systematically is to systematically eliminate. So we're going to say, use equation 1 star to eliminate x from equation 2. And so in equation 2, I know that there's a coefficient of 3, right? So if I wanted to remove x, what do I need to multiply this equation by? 3, right? Or minus 3. So I can write E2 minus 3 times E1 star. This gives me 3x minus y minus 3 times x plus 3 over 2y. And this is equal to, now on the right side I have 1 minus 3 times 4, which is equal to minus 11. Yep. We're good here? Okay. And so now this gives me basically minus 11y over 2 is equal to minus 11 is my equation, right? So my 3x, this cancels, right? And now my third step, notice that I'm being very systematic here. You all can read off the value of y from this equation. But I'm going to say third step is solve for y, which gives me y is equal to 2. And finally, what we're going to say is for back substitute. And let me try to zoom out just a little bit. Okay. Right? So we solved this. Probably some of you solved the problem exactly this way, right? But this is one way of solving it. And so I want to now just compare this and write this exact algorithm in a slightly different form using these augmented matrices. So here I had this augmented matrix, and what did I do? I just divided basically the first equation by 2, which here is the same as dividing the first row by 2. So if I divide the first row by 2, I can represent this step 1 as 2 divided by 1 is 1, 3 divided by 2 is 3 over 2, 8 divided by 2 is 4. And I didn't change anything on the bottom equation, so that's just as it is. Right? That's all I did here. And how would we do that for the second step? Here in the second step, we haven't changed the first equation. It's exactly as it was. But now I'm taking E2 and replacing it by E2 minus 3 times E1 star, right? So when I did that, here I got basically, this was implicitly a 0x plus minus 11 over 2, right? So when I do this operation, what do I get here? I get a 0 here. I get minus 11 over 2, and here I get a minus 11. Right? I'm just representing the output of each of these systematic steps. I'm just drawing them in this table form. And then the last step, I solved for y. What did I do? I got 1, 3 over 2, 0. I divided I scaled this, right, by 2 over 11 to get basically here a 1, and here a 4, and here a 2. And as soon as I saw this 1, I basically knew that this meant 1 times y equal to 2, and I was done, right? I was able to solve. The nice thing here, when you notice, when you look at this, what are you seeing here? You're seeing that there's a triangle that has formed here, right? And you can think about it as stuff above the diagonal is non-zero, stuff below the diagonal is 0. This algorithm that we have just performed, we did it using just operations and manipulations to these equations. Then I rewrote it with some boxes and some lines around it. This algorithm is Gaussian elimination. And this algorithm is what forms the basic fundamental principles behind the linalgebra.solve that we used in the example that we just did in the IPython notebook. So Gaussian elimination, one would think that if this method is named after Gauss, that Gauss was the person that invented it. Turns out that Gauss did do a lot of work on this algorithm, and he is one of the reasons that it is so widely used today. But actually, this algorithm was invented in China more than 2,000 years ago. It showed up in a book, I think, called 9 Jewels of Mathematics, or 9 chapters of mathematical art. It was a book that was written 2,000 years ago in China, but the attribution of this algorithm we always give to Gauss. So something to keep in mind when we're thinking about names. Either way, I hope that I've convinced you that this is pretty simple, right? There's nothing complicated here. And what I want to do is now use this systematic strategy for solving things to go back to answering the question from last lecture, right? What was the question that we left with? How do I know that there's going to be a unique solution to my system of linear equations? How do I know when I've solved stuff, I'm going to be able to, when I've set up my system of linear equations, I'm going to have a solution. Or maybe I'll have no solutions, maybe I'll have infinite solutions. Right? That's exactly what I want to try and figure out. And so that's what we're going to do for the rest of the lecture. But before doing that, I just wanted to point out another representation for this that we will be coming back to later in this class for these systems of linear equations. And remember, we drew this as a box, right? We had this box here, and we called it an augmented matrix form. I'm going to call this matrix vector form. And here, I'm just going to add a little reminder about what the variables are. So I'm going to copy this exactly. And I have my 8 and my 1. So I basically separated this out, the stuff after the line I put here, the stuff before the line I put here. And I'm going to put a reminder that x and y are my variables. And how do I read this? I read this as the variables associated with the first column are at the top of this vector. Whatever variable is associated with the second column is the second element. So if I had more equations and more variables, I would just have a larger stack. But basically, do you see this correspondence? That this is 2x plus 3y equal to 8. And I'm just writing exactly this equation, but in this other form. Okay? Great. Now's a good time to pause and take a question or two. Anyone have any questions? Yeah? Great question. Question was, do you always have to have an upper triangle, or can you have a lower triangle as well? So when you're solving the algorithm of Gaussian elimination, your goal is to get an upper triangular matrix. But as we just saw, there's many, many different ways of solving systems of linear equations. So another way would be to come up with an algorithm that would get you a lower triangular matrix. This could also lead to solving the system, but it would be a different way. So is it Gaussian elimination? No. But is it wrong? Also no. It's just a different way. And in fact, I believe some of the precursors to Gaussian elimination involved generating, writing the equations slightly differently. It involved writing the equations vertically. So we nowadays write horizontally, right? But sometimes these equations were written vertically with the same arrangement. So there were slightly different manipulations, things looked slightly different. This was back in the ancient days when these algorithms were actually being invented. Yes, question? Following up on that, can the triangle be inverted? Again, it is possible for the triangle to be inverted, another different way of solving the system. But again, in Gaussian elimination, the standard algorithm that we will be learning and using, we will be using what is called an upper triangular setup. So this is called an upper triangular matrix. Okay? And our goal will be to try and get this to being in an upper triangular form. And here I just want to label this guy as a matrix. This guy is a vector. This guy is a vector. Okay. So now, since we had our goal of trying to understand, when do systems have, infinite solutions or no solutions, let's try another example. Let's try the following example, where we have example 2. 2x plus 3y is equal to 8. So very similar to the first one. And we have 2x plus 3y is equal to 6. So let's try and do Gaussian elimination on this example, right? Looking at this example, you should already be feeling a little funny, right? It's like, why would I come up with this example? Because we're trying to understand what's going on. So if I want to write this in augmented matrix form, how would I write this? Can someone call out the numbers for me? Great. Now what are we going to do? What is our first step? Our first step is to normalize the first row, right? So what am I going to do? What am I going to get? I'm going to get 1, 3/2, 4, just as before, and 2, 3, 6. Everyone with me here? I divide row 1 by 2. Okay. Now I'm going to try and eliminate x from equation 2. And how am I going to do that? Well, I can take the second row minus 2 times the first row, right? So I can have row 2 minus 2 times row 1. What will that give me? I'll get 1, 3/2, 4, because that won't change. Here I'll get a 0. What will I get here? Oh, thank you. What will I get here? 0 and right? Thank you. So what am I getting here now? I'm getting basically a row of zeros equal to a non-zero number. And so what does this mean, right? In our interpretation, we have this, we're writing it in this form, but really this means 0x plus 0y is equal to 2 or negative 2. It doesn't really matter, right? So how can you solve this? What does this mean? This means that there's no solution, right? So Gaussian elimination, if you put things into an upper triangular form, but you get basically a row of zeros on the left and non-zero on the right, this means you have no solution. So do you see how now, because we're doing it in this systematic way, we can teach a computer how to do this. We can write an algorithm. Whereas if we, sometimes did it so that we had an upper triangular matrix, and sometimes did it so we had a lower triangular matrix, or sometimes did it in some other order, we could still solve it, but we wouldn't be able to teach a computer how to interpret that result. By doing it in this standard way, we can then write software that basically allows you to look at this and immediately tell what kind of system it is. So this says that there's one more type of system that we want to try and figure out. And the last example that I want to do is the following. X plus 4y equal to 6. And let's say 2x plus 8y is equal to 12. So why don't you take a minute to do this one out and just check your answer with your neighbor. So when you try to do the first step, what is the first step? The first step says normalize. If you try to do this first step, normalize, do you need to normalize? It's kind of already done for you, right? The leading coefficient here is already 1. When you look at this matrix here, there's already a 1 here. So there's nothing you need to do. Great. This was easy. So then let's go to the second step, and let's use this row to eliminate x from the second row. So I want to take basically row 2 minus 2 times row 1. So I get 2 minus 2 times 1, which is going to be a 0 here. Here I keep this exactly the same. So 2 minus 2 is 0. 8 minus 4 times 2 is 0. And 12 minus 6 times 2 is 0. So again, I have ended up with this row of zeros at the bottom, right? And this is different from the first example where we did. Because here, you see in this example, there's no operation that you could have done that would have gotten you a row of zeros at the bottom. But as you see in both of our kind of problem situations, this one where we have no solution, and this one where we know that we're going to have many solutions, we have this row of zeros showing up, right? And so this row of zeros is saying that, is telling us something about our equations, right? That we know from looking at them, because there's a few number of equations, what we're seeing is that basically equation 2 is just a scalar multiple of the first equation, right? They're not actually giving you two pieces of information, they're giving you the same information twice. They're not new things. And so what this is saying is that this isn't enough information to give you a unique solution for x and y. In fact, if you were able to choose any value for x, let's say I choose x, what is your favorite number? 3. Favorite number is 3. If you chose x is 3, would you be able to find a value for y? Yes. What about if you chose x is 15? Yes, right? If you chose x is 10 million, you'd still find a value for what y is. So here you have an infinitely many solutions. Many solutions. Let me try and zoom out here. Yeah. So again, here we're looking at this in upper triangular form. And what we see here is now there's this row of zeros. Here also there's a row of zeros, but this guy is non-zero. And these are basically the systematic ways in which we can figure out if there's a unique solution or infinitely many solutions or just no solutions at all. So this is an introduction to Gaussian elimination by example. What I want to do now is formally present this algorithm, because clearly Python does not implement this by example. Each example is not hard-coded. There's an algorithm that's hard-coded, right? So let's try and actually write this exact algorithm out. So in a general setup, when you have many, many variables and many, many equations, let's say you have n variables and m equations. So this means you have, let's say, alpha 1, 1, let me write these. Alpha 1, 2, alpha 1, n, x1 plus x2 plus xn. This is equal to beta 1, and then I have alpha 1, 2, alpha 2, 2, alpha 2n equal to beta 2. x1 plus x2 plus xn, and then I have alpha 1m, alpha 2m, alpha mn, x1 plus x2, xn. This is equal to... Right? The reason I'm taking all this effort to put things in color is, again, it's really important to keep track of what is known and what is unknown. So here, Is this readable? Okay. Yeah, question? Oh, sorry. Yep, you're right. Thank you. Anyway, the point of this was to show that what are these guys? These are the measurements. These alphas are our coefficients, or our experimental design, basically. So these are also known. And the x's, these are our variables. Okay, writing is going to be challenging. Let me try. Okay, so what we're going to do is we're going to write this all into a giant augmented matrix form. So we're going to have alpha 1, 1, alpha 1, 2, alpha 1n, alpha 2, 1, alpha 2, 2, alpha 2n, alpha m1 should be m1, alpha m2, alpha mn, and here you have beta 1, beta 2, beta m, and the way we're going to talk about Gaussian elimination is we're going to talk about it systematically as operations on one row after the other. Okay? So we're going to start with the first row. Start with row I equal to 1. And then we're going to say, first step, one of the things that you have to think about in Gaussian elimination is you have this setup, but what if alpha 1, 1 was 0? What does that mean? It means that the first equation doesn't contain the first variable, right? x1 doesn't show up. So now, what do you need to do to deal with that, right? Our algorithm always said, normalize so that you have the coefficient of 1 for the first variable in the first spot. So there's actually a pre-step that you want to do, and what you want to do is you want to basically swap rows so you have equation with xi in ith row. So when we're starting with I equal to 1, this means that make sure that the first row actually has the variable x1. Then what you do is you make sure that the coefficient of xi in row I should be 1. So this requires multiplying and dividing as necessary. Now, for all the remaining rows, for all of the rows j that are starting from I plus 1 to n, so you take your first row, You normalize it, you make sure that you have the coefficient 1 for x1. Then you take all of the bottom rows, and you systematically eliminate x1 from these other rows, right? In our case, we only had 2 variables, so it was really easy. If you have more variables, you do exactly what you did for the second row, for the third row, and the fourth row, and so on and so forth. So you say use the ith row to cancel xi from row j. And once you've done this all the way through, you update, and then you start with the second row and the second variable, and so on and so forth. You keep going until you get your upper triangular matrix. And then you can see the bottom row there, right? Is it a row of all zeros? It is a row of zeros with a non-zero. Is it basically a row of zeros and then a 1 and then something? This will tell you which situation you're in, how many solutions you have. And once you have that, you can basically solve or back substitute in the case that you have this unique solution. And this is your algorithm. Maybe I can zoom out a little bit to have all of this show. This is basically the algorithm of Gaussian elimination. This is written out in a lot of detail in the notes. Please go and read it. Please make sure you understand it. Ask questions if you have any questions. Okay, let's see how much time I have left. Okay, great. So we're good here? There's basically now, there's the stopping conditions, right? And just to write all of these out very carefully, we have 3 stopping conditions. We can have a row of zeros and a 0. And we know here that we're going to have an infinite number of solutions. We can have a row of zeros and then something else where b is not equal to 0. And here we have no solution. And third option is that we're going to have zeros and then a 1 and then some constant b. And here we know that we have a unique solution. Are these stopping conditions clear? Any questions about this algorithm? Basically, what I want to emphasize is that this is something that is very similar to what you've been doing in terms of solving system of linear equations, just written differently. Question there in the red shirt. Sorry, you have to speak up. I cannot. Yes, so you will see examples in your homework where you might not get through all of the rows. You might end up with a row of zeros early on, and you will end up stopping early. So the question was, do you have to go through the algorithm if you hit a stopping condition early? What if you haven't gone through the entire matrix yet? What if you haven't touched all of your rows yet? And the answer is that these stopping conditions will terminate you if you hit them early on as well. I know that there was a question back there. Yeah. Isn't the number of rows m not n? So if you have m equations, you have m rows. Yes, thank you. Good catch. This should be m. Thank you. Other questions? Yes. Great question. Can you explain what upper triangular matrix means? So whenever I say upper triangular matrix, I mean a matrix of this form, where when I look below the diagonal, all I have is zeros. So above the diagonal, there can be zeros above the diagonal too, but below the diagonal, they had better all be zeros. So even if this was not a zero here, that would still be an upper triangular matrix. Yeah. Okay, last question. The question is about, are there conditions between m and n? And turns out that Gaussian elimination will actually be robust. Try it out, you'll see. And you'll see examples of this in discussion, and how to deal with more equations and less unknowns and so on and so forth. You'll find that you'll end up in these situations where you have either no solution or infinite number of solutions if your m and n are mismatched. Okay, so now I want to move finally to talking a little bit about something that is a different perspective on systems of linear equations, which is a geometric perspective. And let's start with the example that we, did first. So we have 2x plus 3y equal to 8, and we have 3x minus y equal to 1. This was our E1, and this was our E2. And we know that a linear equation like this can be represented as a line in a two-dimensional plane, right? So how does our understanding of Gaussian elimination connect to this geometric perspective? So for this, I want to just plot this out. So let's say I have my x-axis here and my y-axis here. And I have some units. My x-axis. Okay, and so 2x plus 3y equal to 8. Here I can put x equal to 0, which tells me that y is 8 by 3 equal to 2.66. And if I put y equal to 0, this tells me that x is equal to 4. So I know that, let's say for my first equation, I'm going to have basically x0, y is 2.66. So I'm going to have x is 4 when y is 0. And so this line, this is my E1. This point is basically 0, 4. This point is, this is 0, 2.66, and this is 4, 0. Right? I can graph this equation as a line. And what about the other one? I know there that if I put, for this one, I can say that if x is equal to 0, then I know that y is equal to minus 1. If y is equal to 0, I know x is equal to 1/3. So again, I have 0, minus 1, and 1/3, 0. So I have a point here, and I have a point here, and this is my line. And so what is the solution that I have for these two systems? This is 2, 1, which is exactly the solution that you recovered when you solved these, right? Oh, 1,2, sorry, good, thank you. And so we can see that basically, since we're talking about linear equations, they can be represented by lines. And we can see that, okay, well, the first equation allows motion along this blue line. The second equation allows motion along this orange line. Where they intersect is basically a solution. So now, how would you think about the case that there are no solutions for a system of, if you had parallel lines, right? If I was to take this orange line and rotate it to be parallel to the blue line, then you'll see that these are never going to intersect, which means that there's never going to be a solution. What about an infinite number of solutions? If the lines were right on top of each other, right? And so this geometric perspective is something that holds not only in 2 dimensions, but it also holds in much higher dimensions. And it's a perspective that we will build on because we are going to start talking about linear transformations. And when we're talking about linear transformations, we want to keep this geometry in mind. And so basically, when we're manipulating these equations, we're basically looking at them as different lines. So one of your TAs has actually made a really great demo that I will share with everyone, but I wanted to show it to you here. Could I have this again? Okay. The question was, for infinitely many solutions, a plane also works. Absolutely. That would be in a situation where you're considering an ambient space that is 3-dimensional. Then you could have infinitely many solutions in a plane. Alternatively, you could have basically no constraints in a 2-dimensional space, and you could still have infinitely many solutions in a plane. So that's definitely possible. So what you have here, what some of your TAs have done, is it's an interactive Jupyter notebook. And this is basically showing you that you can try and figure out how systems are going to behave by looking at them geometrically. And we've been writing systems as basically in this format. Oh, I can't see it here. Never mind. We've been writing systems as a times x plus b times y equal to some constant c, right? But we can also write them in a format that is a slope and intercept format, right? That y is equal to m times x plus c, where m is your slope and c is your intercept, right? You can just divide to rewrite these in different formats. So this is written using basically the slope and intercept format, and it draws out this point of parallel lines. So what this allows you to do is you have actually, I might have to restart this. Let's see if this runs. Yeah. So this basically plots 2 equations. The first is y is equal to, can everyone see this at the back? Is 2 times x minus 1, and this other one is y is equal to minus 3 times x plus 1. And as you basically play around with the slopes, you can see that, can I adjust it to be exactly parallel? For example, if you have parallel lines, they're never going to intersect. But as I change the intercept, I can get it to be actually an infinite number of solutions. Or as my intercept moves off, I still have no solutions. If I change the slope on the other line, I can actually have a unique solution. So this is something, it's a tool that we will put up on the website that you can play with, that you can try to build on. Perhaps you can also try to explore this in 3 dimensions. So with that, I'm going to end for the day. If you have questions, please come to office hours, follow me right after, and please look into submitting your homework. Thank you.